let's discuss the Riemann sum. Now, just a little bit of warning, this is going to be very abstract, so bear with me. Got a lot written out here, and as we go through each point, I'm going to do my best to really illustrate and so we understand what's going on. So Riemann sum, the goal is to be able to find the area under a curve. So we're going to start with a bounded function f on a closed interval. So I'm going to draw just a little curve here on some closed interval a to b. Our goal is going to be to find the area under this curve. Now, the way we found areas before was by using rectangles, by creating rectangles. We're going to be doing that exact same thing. It's just that we want to be able to not specify how many rectangles we're going to create at the beginning. So I'm going to have to do everything very abstractly. I'm not going to use any numbers as we go through this. So the first thing we're going to do is we're going to subdivide into n subintervals. So we're going to have n different rectangles. And these are not necessarily going to be even in width, it doesn't matter. And to do this, we're going to choose points x1, x2, x3. So again, just find kind of for some examples, x1, x2, not necessarily even, they might be, it doesn't matter, x3. And so notice by choosing 3 or n minus 1, so 3 subpoints, we have 1, 2, 3, 4 intervals. We always want to have n intervals, and we get that by using one less break point in between. So now what we see is that we have a less than x1, less than x2, less than x3, kind of everything ascending from a to b. And then for notational consistency, we're going to replace this a with x naught, x with a subscript of 0, and b, and let it be xn, just so we can have everything in terms of x's. They're all just x coordinates, so we've just made that simple little replacement there. So we can see x0 is less than x1 and less than x2, all the way up however many we have, and again we could have more than 3, it's just I've chosen to break it up into 4 rectangles currently. This set of points is called the partition of the interval. So we've partitioned the interval up into these 4 subintervals using these 5 points, one being the initial a, one being the terminal b. The partition divides the interval into n subclosed intervals, closed subintervals, excuse me. We have subintervals, this should be a bracket, subintervals that start at x0 and go up to x1 from there. This symbol right here, I'm trying to get to be a bracket, I might just leave it. They should all be brackets right over the top of it. The equation editor in Microsoft is not great, so I might just change that on my paper. So we see that we have a subinterval x0 to x1, x1 to x2, x2 to x3, and so forth, however many we have. Now, somewhere in here we're going to have the kth interval. And so it could be whichever ones, right? So it could be the x2 to x3, it could be x3 to x4. And so just somewhere in here we have a subinterval xk to k minus 1 rather to xk. And the only stipulations on these k's, they at a minimum have to be 1, because if we're going to have that 1 minus 1, the smallest we can possibly have is 0, 1 minus 1 is 0, and the largest of the k's can be is n, so that would be this last interval, x3 to xn. I'm not using any numbers for these k's because I don't want to specify which interval I'm at, because I want to be able to do it for any of them. So the xk is just the kth interval. Now the width of that kth interval would just be gotten by subtracting the 2x values, so the larger one minus the smaller one, and we call that delta xk, that would be our width. And then just for a little side definition here, this isn't falling directly in the flow of what we're doing, but we need it. The norm of the partition, which we indicate with absolute values around p, is the largest width of any of these subintervals. So based on my drawing, it appears that x2 minus x1, that would probably be the smallest. This x3 to xn, that would probably be the largest, so that would be the norm of the partition. We can find a point ck in any of these subintervals. So right here, there would be a point, call it C2, just for a point. This could be C1, C0, and each interval we have a point somewhere in there. Now, could it be right alongside the edge? Sure, it could be anywhere. It doesn't have to be split. There's no stipulations on C other than it is in that generic interval. And then on each subinterval, we can draw a rectangle. And so I've already kind of done that. I've put those endpoints on there, but I just got to form a top and a bottom. And the way I'm going to form that top and bottom is based on that CK. So that C happens to be right there, then that will give me my height. So that would be one of my rectangles. If that C is right there, that'll give me the next rectangle. If that C is right there, well then that will give me my next rectangle. And so that C is just some point inside, but I'm using that to get to my height, wherever it might be. And again, C doesn't have to be in the middle. I could choose it to be right there, and that would be my rectangle. And now that we have a width and we have a height on each rectangle, we can find the area of any of those rectangles. And we call that AK for the kth area over the subinterval, the kth subinterval. And we find that by using the height, or the function's value at that C point, times the width, which we've already defined as x sub k. By adding together all these rectangles, starting with the first interval up to the last, by adding up all those areas that we just found in the previous equation, we get the area under the entire curve. We've done this when we were doing the area of finite sums. It's just now I'm not specifying how many rectangles I'm using. I'm using a completely generic equation. So we can now write this S sub p equals, p representing the partition, the summation k is equal to 1 to n of f of ck times delta xk, representing the height and the width. Adding up all of those rectangles, we get the sum. And this sum is called the Riemann sum. And so we're going to do an example with this, but why does this help me? Why does not specifying how many rectangles I have and leaving everything generic help me get to an area under a sum? So what we saw before when we were doing our finite approximations is that 4 rectangles was better than 2, but 4 is more work than 2. And we said, hey, if we could go up to 100 rectangles, that would be better still. That would be a more accurate area, but 100 would be a pain in the butt. So now we have a very nice little formula for writing out however many rectangles we want. So if I want 100 rectangles, I'm going to put 100 there. But again, still kind of pain just to multiply those things together. But now, because it is in this summation form, there are certain formulas we have with that summation that allow us to simplify our work and get to a nice equation a little bit easier. And we're going to see that in just a minute. The other thing to note is that we said long term what we'd like to do is not really just to even have 4 or 10 or 100 rectangles or 1,000 rectangles. We'd like to have infinitely many rectangles. We'd like to get to that infinity. And so now, because we have this nice little formula for it, we can begin to think about what infinity is going to look like. So let me go ahead and set up an example. So what I want to do is, for the function f of x equals 2x squared plus 1, I want to find a formula for the Riemann sum obtained by dividing the interval 0 to 1 into n equal subintervals and using right-hand endpoints for each height. Then we're going to take the limit as partition approaches 0 to find the area under the curve. Let's start by just finding that Riemann sum. So remember that Riemann sum, SP, is equal to the summation, okay, is equal to 1 to n of the height of each rectangle times the width of each rectangle. So we need to start there. We need to get the height and the width of each rectangle. Well, the height is this equation right here evaluated at the point k. Because my starting point is 0, each time our delta x goes up by a little bit, that's going to give us that next height. So we're going to use the equation 2, and then we're going to replace our x there with something in just a second. 2x squared plus 1. So what is that height? Well, initially it was just 0, so we plug in a 0 there, but then it's going to change by some amount between k equals 1 and n until we get up to that final value of 1. And so what is that amount right there? Well, it's the width of the interval. It's however many times we've added the interval. And so that would be the 1 minus 0 over n times the kth portion that we're looking at. So each width itself is 1 over n, however many rectangles we're using. And how far along we are in the interval from 0 to 1 is determined by the kth 1 over n that we're at. So this would be our equation for the height, and then the width is very simply just the 1 over n. So again, the height's the tricky part. And the way we can think about it is we always start at the initial point. So we always have an initial x value of 0. And then to that I add the width times the k, because the k is moving me over by each little bit of width each time. And so now I'm going to simplify this. So we're going from still k is equal to 1 to n. We're going to have the 2 times k squared over n squared plus 1 times 1 over n. And I can distribute that 1 over n, and I can also break apart the sum because we have our rules for summations. We know we can always split those sums apart. So we'd have 2k squared over n cubed plus 1 over, sorry, I need a summation. Summation k equals 1 to n of 1 over n. Now in the first one, we can pull the 2 over n cubed to the front because that is just a constant. And so we have left in our summation the k squared. And then the second one, well, that is just a constant inside the summation. And so remember what our rules say for that. If we have just a constant, we just multiply it by the n. So we'd have plus 1 over n times n. So that one's very easy. And then we also have a formula for the first n squares. And so we'll have 2 over n cubed. And the formula for the first n squares of a function, n times n plus 1 times 2n plus 1, all over 6. Then 1 over n times n is just a 1. And so I can do a little bit of cleanup. I know that 2 goes into 6 3 times, and so I can simplify that. I'll have a 3n cubed on the bottom. On the top, if I multiply those together, 2n cubed, we'd have n plus 2n more is 3n, and then times the other n is 3n squared. Then we'd have a 1n. And we can simplify that a little bit more by dividing out the n's. So we'd have 2n squared plus 3n plus 1 all over 3n squared. And I forgot the plus 1 above. I need to include it here too. And so there is my formula for the Riemann sum with the unknown n number of rectangles. Now, if I was using the right-hand endpoints, we did a similar example in the finite sums. We could just plug in however many rectangles we wanted. So if I wanted to know what this would say with 3 rectangles, we'd plug in 3, we'd solve. If we wanted to know with 15, we could plug in 15, we could solve. Really, the whole reason doing all this work and getting a very generic formula is so that we can take that limit as the partition goes to 0. So remember what the partition, or the norm of the partition, remember the norm of the partition is the largest subinterval. In this case, we already said they're equal. But the nice thing about this limit of the subinterval, if we're driving that largest one to 0, that means all the smaller ones are also being driven to 0. So if we didn't have equal subintervals, it wouldn't matter. That's driving them all to 0 anyways. And that means the endpoints really don't matter either, because if we're driving each interval to 0, the left endpoint becomes the same as the right endpoint. They're all the same. Every point along there is the same. And so now what we're going to do is we're going to look at the limit of this thing. And what does it mean if the norm of the partition is going to 0? The only way we drive those subintervals to 0, and it started at a height of 1. The only way we drive those subinterval widths to 0 is if we just keep adding more and more rectangles. If I just keep adding more and more rectangles, what am I doing? I'm really letting n go to infinity. So we finally are getting to this idea that we can find the exact area under the sum. We're basing it, this is kind of a crazy idea, we're basing it off an approximation. These areas using rectangles are an approximation. But as soon as we say, well, let's try and have an infinite number of rectangles, we actually do get the exact area under the curve. So I'm going to take the limit as n goes to infinity of this thing that we just found, this formula that we just found. And so however you feel comfortable simplifying these limits, I know that this is just going to give me 2/3 plus 1, which will be 5/3 or 1 2/3, but that's my answer. Thirds, not halves. That is the actual area under the curve of this 2x squared plus 1 between 0 and 1. We actually have the exact area under the curve now. We did it based on an approximation, but because that approximation, we're letting the partition go to 0, we're taking an infinite number of rectangles, that means our approximation has actually become infinitely accurate, meaning we actually have the area under the curve.